Today's topic is cryptography. And what I want to do actually, the first thing that I want to do is to set some expectations. So for today's lecture, we're not going to be talking about cryptocurrency. However, by the end of this lecture, you should have a very good understanding of crypto basics, the cryptographic goals, and also we're going to take a look at some popular crypto algorithms that are implemented as countermeasures or, algorithms to secure our communications. And lastly, we're going to conclude this lecture by implementing one of these popular crypto systems in Java, and if time allows, we're also going to implement it in C++. So you're going to see how we can turn the idea of what it's known as a crypto system and to encrypt or decrypt or to make something secure. How can we actually turn that into an application? So we're going to see that in practice. Okay, so actually before I begin, I would like to take a look at this map. Let me pull that out. So the map is right here. Okay. So this is the live cyber threat map. So basically, right now you're taking a look at live attacks that are being conducted all over the world. Attacks could be malware attacks, phishing attacks, exploit attacks, or any other types of cyber attacks. And this is telling us that our communications or the network is definitely subject to various types of attacks. So therefore, there should be some type of countermeasures, security countermeasures implemented. And that's where cryptography comes into the picture, right? So we are aware that there are various types of attacks and our network is subject to them. Therefore, we should implement some security measures. And the study of cryptography is what's that for? So going back to our lecture. So I provided you with a link if you guys want to take a look at that threat map later on. But first, let's get started by defining what cryptography is. So cryptography is a method of protecting information and communications through the use of codes, right? So that only those for whom the information is intended can read and process it. Now, here, the word crypto comes from the Greek word kryptos, and it means hidden. And cryptography is a composite word, and the prefix crypto means hidden, like we said earlier, or secret. And the suffix graphy stands for writing. So in total, we're talking about secret writing here. So cryptography is a composite word, and in computer science, it refers to secure information and communication techniques that are derived from mathematical concepts and algorithms. And all of this is just to transform messages in ways that are hard to decode, right? So we're communicating over the network. We want to make sure that our communication is secure. We want to make sure that we are immune from, cyber attacks like, eavesdropping or man-in-the-middle attack. And we don't want anyone to tamper with our communication. So some of the communications tend to be very, very, need to be very, very secure, especially like if you're conducting like transactions, banking transactions, financial transactions. You want to protect your identity, like your password, username, and so on, right? All of that is sensitive data that needs to be made secure. Earlier, cryptography was mainly focused on the encryption, right? So encrypting means transforming a plain text into a different format that is not easy to read by just looking at it. However, modern cryptography goals are confidentiality, concerned with confidentiality, data integrity, non-repudiation, and authentication. We're going to take a look at all these goals and explain what they're for and what needs to be taken care of. So the first goal here of cryptography is confidentiality. And it was the original purpose of cryptography. Confidentiality was the initial purpose of cryptography. And it means that if the data is confidential, it cannot be read or understood by anyone other than the intended recipients. So it is achieved through encryption, and both symmetric and asymmetric encryption can be used. And we'll discuss these later, by the way, asymmetric and symmetric. We're going to see the difference between them, and we're going to also mention examples. And the second goal is integrity. And what it means is the information cannot be altered. Actually, in a nutshell, information cannot be trashed without being noticed. And a better description of that is that it means that information cannot be altered in storage or transit between the sender and the intended receiver without the alteration being detected. So if any change has happened to the data, the goal of cryptography is to detect that change, okay? And hash functions when we say hash functions, we're talking about cryptographic hash functions. So crypto hash functions are a way to ensure data integrity because they serve as a checksum or a way to for someone to identify whether data has been tampered with after it has been signed by the sender. So for example, let's take a look at a scenario. Let's say you've logged on to a public Wi-Fi, let's say like the Starbucks Wi-Fi or something like that. It's a public Wi-Fi and you want to send me an email. By the way, don't do that because it's very insecure to send an email through a public network, or let's say conducting a banking transaction through a public network. It is very insecure. So you write out the message, sign it, using, let's say, your digital certificate, and send it on its way across the internet. So this is what you might call as, man-in-the-middle territories. We're talking about this public network. That's the territory of man-in-the-middle. Man-in-the-middle will conduct these cyber attacks. So meaning that someone could easily intercept your message and modify it to suit their evil purposes, right? So suppose that you're conducting banking transactions through this public network, or you're sending me an email, like in our example, through this public network. And let's say someone is, spying on our communication because they could, because this is an insecure type of communication. They could tamper with our communication, right? So, however, we should implement some type of measures to detect that our communication has been tampered with, and that's what data integrity is concerned with. So the example here is of a digital signed email that's been, manipulated in transit via man-to-man in the middle attack. So we're talking, you are sitting at Starbucks and you're using their public network. You sent me an email. However, someone conducted an attack, which is that man in the middle, and they modified something in the email that you're sending me. So the hash digest changes completely when any of the email content gets modified after being digitally signed, signaling that it can't be trusted. When you say hash digest, by the way, it's, you have a hash function. It takes your message as the input and it's going to hash it. And when it hashes that, it's going to hash it into what is called a message digest. A message digest is a fixed size output, right? So it does not matter the size of the input message, does not matter how big is your email that you're sending. Once it's hashed, depending on the hash function, of course, it's going to be hashed into a fixed size output. Okay, so right, so now that I received the message, right, and I want to know if it's legitimate, what I could do then is that I will use the same hash function that you have used and create a hash value, a second hash value, and compare it with the hash digest that you sent me and see if they're the same. If they're not the same, I basically say, all right, there has been a change in the message that you're sending me. Therefore, it could not be trusted, right? Therefore, there's someone maybe conducted an attack. And by the way, even if it is a very tiny change in the message, like you capitalize a letter instead of using one that's lowercase, or you swap, let's say, an exclamation mark with a question mark, it's going to result in the generation of an entirely new hashed value, hash digest. So any change will be detected when using hash functions. But that's the whole idea. No matter how big or small a change, the difference in hash value will tell you that it's illegitimate. What happens if there is a hash collision? That is Kelvin's question. And when you say hash collision, you mean, what do you mean by hash collision here? Did you mean, so because when you say hash collision, because here we're talking about a hash value that's being generated by the sender, that's the message digest, and I'm generating my own hash value as the receiver. So I'm going to compare the two. There are two types of collisions, by the way. There's a weak collision and there's a strong collision. And it means that, of course, it is, yeah, I think I understood what you meant. Hash collisions exist. However, we're assuming that it's a very low chance that a collision would exist. And by the way, attackers are the ones looking for hash collisions, because once they find these collisions, they will be able to analyze this hash function. They will be able to understand how the hash function works, and they will be able to find out original messages in the future, right? So collisions are really what attackers are looking for, right? So we're assuming that there is a very low chance in collisions occurring. However, they may occur. It is possible. Nothing is 100% secure. And we'll take a look at hash functions in a future slide, and we'll talk more about this. So for sure, I'm glad you guys know about hash collisions, especially there are two types: weak collision and strong collision. The other goal is non-repudiation, and that's is basically the mechanism that proves that the originating node sent a message that and that the receiving node received it. So therefore, we're saying that the sender cannot deny sending a message, and the server cannot, the receiver, sorry, cannot deny having received it, right? So for example, like you're making a banking transaction, you say, I made a transfer. So let's suppose you conducted this transaction. You made a transfer of $500 to your friend, and later on you deny that you've made that transaction. You say, "Oh, I only made $50 transaction," right? So non-repudiation is the goal of cryptography, to ensure that the sender cannot deny sending a message and the receiver cannot deny having received it. So non-repudiation can be accomplished through digital signatures, confirmation receipts, or timestamps. These are three different ways to accomplish non-repudiation. I don't know if you guys have heard of digital signatures. Usually, like websites get to be registered with a certificate issuing company and so on. That is just to ensure the authenticity. And usually these certificates get to be renewed every year and so on. So like, for example, Amazon.com. If you actually open up Amazon.com and you're going to see that lock icon next to the URL, and you click on it and it will show you, let me actually show you what that means. So for example, if you go to Amazon.com, so Amazon.com. Okay. So Amazon.com has a certificate. So if you see this lock right here, so if you click on it, it tells you that the certificate is valid. And usually, it's not you as a user who's checking for these certificates and so on. It's really your computer, your client. That's the client that is checking if the server that they're communicating with have a legitimate certificate. So this certificate, for example, when you click on it, it is issued by, the G-Cert Global, let's say CAG2, and it is issued to Amazon.com, and it's valid from this date to this date, and so on. So that's a certificate. It's a digital certificate. And usually, hash functions are used to, generate digital certificates. So the fourth goal, which is a very, very important goal of cryptography, is authentication. And usually a sender and receiver can confirm each other's identity. And in other words, proving sender and receiver are who they claim they are, right? So you're claiming that you are, let's say, Amazon.com. There should be a protocol that's going to be implemented to check if you are who you claim you are, right? So these are authentication protocols, and they usually work in different ways. They're not all the same. And if you guys are aware of or familiar with the OSI model, Open System Interconnection Model, that's in a networking course you take. So these popular protocols that I mentioned here in this list, they actually don't get to be implemented on one, or let's say only one specific, let's say, part of the communication process. So, the OSI model is a layering approach for communication. So there's, let's say, 7 layers. There's the application layer, there's the presentation layer, session layer, there's the transport layer, there's the network layer, and then there is the data link layer, and there's the physical layer. So all these layers, you could implement authentication protocols in different layers. Not saying that you must implement a protocol in each layer. However, if you implement a protocol, let's say at the application layer, the authentication protocol at the application layer, then we're assuming that it is the application developer or the software engineer's job to make sure that there is an authentication protocol implemented in the application, right? But there are other protocols that could be implemented, let's say at the, let's say, IP layer, which is data link layer, or network layer. Then we're talking about the operating system's territory. And if it is there, then it's the operating system that's going to implement an authentication protocol. So therefore, the application developer does not really need to worry about implementing it into their application, right? So it's like, it relieves them from adding some more work to their application. So these protocols could be implemented at any layer. So for example, here we have SSH, which stands for Secure Shell Protocol. There's SSL, Secure Socket Layer. There's IPsec, which is usually at the IP layer. That's an operating system territory. Kerberos, which uses symmetric key crypto. We're going to talk about it in a second. And then, of course, we have wireless protocols like WEP and GSM and so on, right? WEP is known to be the Swiss cheese of security protocols. It's heavily flawed. However, there are successors and much better protocols. Does the checksum on the application layer count as cryptography? Take income. For sure, yes, but you should always think of cryptography is a huge area. We're not just thinking that cryptography is about authentication or about, so there are various goals for cryptography. So yes, for sure, that is one goal of cryptography, and that is part of cryptography when you talk about at the application layer using a checksum. And you checksum, that means you're doing hashing. Um, hey, Swiss cheese is delicious. For sure, delicious for those cheese lovers, for sure. Okay, and in this slide, I'm actually going to talk a little bit about the basic terminology for crypto, and then we're going to take a look at how we can speak crypto, and then we're going to start talking about the three main areas of cryptography. So we're not talking about goals anymore. We're talking about, techniques, and that's going to be in the next few slides. Amadou does not like Swiss cheese, Gene, so I guess you have a disagreement there. Okay, so basic terminology is that plain text is the original message that you're sending. If you are sending a message, let's say your email, whatever, you're in a chat, let's say you're chatting with someone, sending a text message, or you are simply sending a command or an operation or a request, all of that is considered the original message, and it is usually in plain text. And once it's encrypted, it's basically turned into what's called a ciphertext. A ciphertext is the original message, but it's in a coded format. And if someone, let's say, like gets the ciphertext, it's, let's say the attacker is looking at a ciphertext, they look at something, they don't really know what the original meaning of it. It's like meaningless to them unless they know how it was encrypted and some of the other parameters as well. And the cipher is the algorithm that we use to turn an original message to a ciphertext. So remember, this is terminology, and knowing how to speak crypto definitely make you look good. Especially if you're like for applying to I don't know, cybersecurity job, or you're applying for an internship. And when you speak in this terminology, it definitely makes you look better and makes you look that you know exactly what you're talking about, and that's a better way to market yourself. So, and the key is just another parameter. We're going to talk about it once we look at an example of a crypto system. So a key is just a parameter of a cipher, right? It is used once once applying a cipher, one of the parameters is the key value. Usually it's an integer value in some ciphers, but not all. And the word encipher here is nothing but the meaning of encrypt, right? To encipher is to encrypt, means converting plain text to ciphertext. Decipher is to decrypt, that is converting ciphertext from plain text. Cryptography here is what we're studying, is a study of encryption principles and methods, techniques, and goals. Cryptanalysis, this is the attacker's world, right? That is learning or studying how to decipher or to decode or to decrypt a message without knowing the key, right? Without knowing a key, you will be able, let's say you're going to try to, break this, system without knowing the key. So you're looking at a ciphertext, you start guessing, right? Trial and error, right? So that's called code breaking cryptanalysis. And cryptology is just the study, the science of cryptography and cryptanalysis. So you're talking about how to make let's say communication secure, that's cryptography, and how to break these systems. Also, you study that. Sometimes you really need to think like an attacker to make a system more secure, right? So you need to just think, okay, how would an attacker break my system? Let me pretend that I'm an attacker and try to break my system. And once you've discovered, let's say, like a flaw in your let's say crypto system, or you've discovered like a loophole or a way that the attacker may exploit, and conduct an attack, then you will implement, let's say, a patch or a fix or improvement to your crypto system. So how to speak crypto? Again, it's important to know how to speak it. So make sure you guys speak crypto, and even in, let's say, like if you're taking any of Dr. Callahan's other classes, just today I'm going to teach you how to encrypt your messages. So I'm not going to teach, I'm not trying to teach you how to cheat. However, if you want to trick him and let's say send a message to one of your friends and you don't want him to be able to read the original message, then encrypt it. He's not going to know the original message. Don't do it. I'm just kidding. Okay, so a cipher or crypto system is used to encrypt the plain text. Maybe I'm not going to go all these points, but probably the last 2 points here, because that's what the next few slides are. Anwar, we're not going to try to decrypt this yet. We'll try to do it later. So just keep that in mind. But you need to tell us what crypto system you're using and a key as well. Okay, Dr. Callahan, yes. So asymmetric key crypto system, by the way, this is important. Asymmetric key crypto system is different from a public key crypto system. And we're going to take a look at those in more details in the future slides. But for now, know that asymmetric key it uses the same key for encryption and also decryption. And the public key crypto system will use a pair of keys, one for encryption and one for decryption. So let's take a look at those in more detail. So here we're talking about, so cryptography, right? There are various techniques, and these are 3 types or flavors of cryptography. So there's symmetric key cryptography, there's asymmetric key cryptography, and of course hash functions, which we mentioned earlier. Let's start by taking a look at symmetric key cryptography. So symmetric key cryptography, the main idea here is that you have one key that is going to be used to do the encryption, and that same key will be used for the decryption. And it's and usually this is a major drawback of symmetric key cryptography, because establishing or exchanging this key over the network is a challenge. Because if you're sending, let's say, this key to your friend, let's say in China, you say, let's communicate using this key. Let's use it for encryption and decryption. When you send that key over the network, someone may be, let's say, you know, doing packet sniffing or like, you know, spying on this communication and may get a copy of that key as well. And then, you know, whenever you guys are communicating, he'll be able to decrypt those messages as well. So usually what happens in a symmetric key crypto system is that the 2 communicating party, let's say like the sender and the receiver, will meet physically in person, right? And then they will agree on a secret shared key. And they say, all right, here's the key. Let's use it for our communication. And then the other person just travels to, let's say, whatever country in another part of the world. The only 2 people that know the key is you and that person. And you guys can use that key to communicate. Now, another actually drawback of this is that if you're using symmetric key crypto, it means that if you're communicating with like 1,000 people, you have to establish a shared secret key with 1,000 people, because you have to make sure you establish a key with every single one of those people. And that means you're going to meet with those people, you know, and also how many keys are you going to keep track of? Like, you're going to have thousands of keys, and every time you want to communicate with one, you'll be looking up their keys so you can communicate with them and so on. However, there are other, you know, layers added to this type of cryptography to make it even more efficient. And some types of crypto systems that are using symmetric key, for example, advanced encryption standard, there's RC4, there's Blowfish, there's stream ciphers, black ciphers. We talked about, today we're actually going to talk about one of those examples, maybe 2. They're using symmetric key. And the next type of cryptography or technique is called asymmetric key cryptography. And the main difference between asymmetric and key sorry, but made the difference between symmetric key cryptography and asymmetric key cryptography is the number of keys. So in asymmetric key cryptography, we have a pair of keys, two keys. One key that is called the public key will be used for encryption, and one key that is called the private key is going to be used for the decryption. Now, one thing you should know is that the public key is going to be known to everyone in the network. So for example, let's say we have Bob and Alice. Let's say this is Alice and this is Bob, and they're communicating over the network. So Alice wants to communicate with Bob, wants to send a message to Bob. Bob will have a public key that is known to everyone in the network. So everyone wants to send a message to Bob, will take that public key of Bob and encrypt the message with it. The idea is that only Bob is going to be able to decrypt that message using his private key. However, everyone in the network will use Bob's public key to encrypt. So when encrypting, the key is known to everyone. But when decrypting, only Bob has a private key that is going to be able to unlock that message. Attackers will have the public key as well, for sure, yes. Because really, like for you as as Bob, you don't care, who uses your public key. They're just sending you a message. Later on, you're going to just unlock it and see what's in there. So, but your question, Remington, kind of, raises the, another idea, is saying, okay, what if let's say Trudy here wants to conduct a man-in-the-middle attack. Let's say wants to interfere with Alice's communication with Bob, because Alice is going to take a message, is going to encrypt it using Bob's public key and send it to Bob, right? So Trudy here could interfere and say, you know what? I'm going to send a message to Bob, and I'm going to pretend I am Alice. Okay, well, it's possible, right? It is possible. However, I mean, we're talking about no other security protocols implemented. Remember, we said cryptography has 4 goals. One of those goals is authentication. There are protocols that are implemented to authenticate if this is Trudy or this is Alice or this is Bob, who's really sending the message. So there are protocols that make sure that this is legitimate and it's coming from Alice. So there are some algorithms that are used for authentication, algorithms used for encryption, and so on. In this example, we're only talking about encryption. So if we're encrypting, means we don't want, let's say, Trudy to know the contents of the message that Alice is sending to Bob. So when Alice encrypts the message using Bob's key, Trudy is not going to be able to know the original message. It's not going to be able to decode it. But it's going to see the ciphertext. It's going to see the encrypted version of it. It's going to be able to see it. However, it's not going to be able to decode it because she does not have the private key that only Bob has. So think of a public key as if this is like a box with a lock on it, right? I cannot draw a box here. So I'm just going to just think this is a box and has a lock on it. And it is open to the public. It's an open box. Everyone wants to send me a message, put it in this box, unlock it, right? That's what Bob is saying. However, only Bob is going to have the lock to open that box, right? And that is the private key that Bob has. Yes, excellent, Anwar. So yes, so the original message is not going to be read by an attacker, let's say that is eavesdropping or conducting a man-in-the-middle attack. So Alice is going to encrypt it using public key of Bob, and only Bob is going to be able to unlock it using or decrypt it using his private key. So Trudy, the attacker, was going to see the encrypted version of it, but is not going to be able to unlock it and know the original message. So popular, asymmetric key crypto systems are RSA, DSA, PKCs, etc. We're not going to talk about all of these, but those are just examples. You guys can go online and explore on those. But a popular key exchange algorithm is called Diffie-Hellman. So think of this. So in order for Alice and Bob to communicate securely, remember we said earlier that Trudy is going to be able to read that message, the encrypted version of the message. However, let's say when we apply Diffie-Hellman algorithm, which is a key exchange algorithm using public key and private keys, Alice and Bob will establish some type of a shared secret key that is going to be used for encoding and decoding. And that's going to take us back to the symmetric key cryptography. It starts as asymmetric using two keys, but once the key is established over the network, then we're now talking about symmetric key cryptography, right? Because we have established, instead of meeting in person somewhere and establish, let's say, a shared symmetric key, we've established a shared symmetric key over the network. We started with a public key and a private key. Once we have established a shared information, a secret information, now we can use that to communicate. Let me just say it one more time. Is that the first, the first thing that Alice and Bob are going to do is that Alice is going to use Bob's public key to send Bob some crypto proposal, right? It's going to say, hey, Bob, let's use this as our shared secret key, okay? And she's going to lock it in using the public key of Bob. Bob is going to unlock it and is going to take a look and say and read what Alice is suggesting. And what is Bob going to do? He's either going to accept that proposal or he's going to propose something else. Let's say he accepts. So what is Bob going to do in order for him to send his okay to Alice? He's going to take Alice's public key and encrypt his response. And Alice is going to be able to find out if Bob has agreed or has proposed a new key. Now, once that key exchange process has been concluded, now we say we've established a shared symmetric key over the network, right? See that challenge that we had earlier? But with public key crypto, we can establish a shared symmetric key. Eugene says, and this kind of cryptography depends upon the difficulty in factoring huge prime numbers. So study hard in discrete mathematics. Sorry, I mean the prime factors of huge. Yes, absolutely. So Diffie-Hellman uses, a formula. You guys can explore that online. Uses a formula. It involves mod and so on. However, it also involves prime numbers. So it's like a mathematical operation that's going to be conducted to establish these keys. So when I say public key, it looks like a physical key here. However, it's actually a mathematical equation, that calculation that's going to happen. Okay. And only, let's say, Bob and Alice can inject some of their ingredients into there so they can get the same results. It's a lot more than this, but you can't just, it's like a whole, area of cybersecurity. So you can't just, learn everything in just like half an hour. Usually it's like composed of various chapters. And cryptographic hash functions is the other technique that we talked about earlier. So before I go over hash functions, I see a question here from Charlie saying, what would be benefits of symmetric key over asymmetric? I don't want you to confuse it. It's just that your goal is always to communicate using symmetric keys. Means that you have established the same key to encrypt and decrypt. However, the challenge earlier was, how can we establish a shared secret key over their network without someone getting a copy of that key? And the idea is that we're going to use a key exchange algorithm like the Diffie-Hellman algorithm to establish that key over the network, right? Remember earlier we said asymmetric key crypto is that you sit down somewhere in a closed room and agree on a key. But if it's over the network, it becomes a challenge, right? So establishing the key or key exchange over the network will be done using public key crypto, that technique, okay? Okay. And so hash functions, we talked about hash functions earlier. However, you should remember that hash functions are a one-way cryptographic algorithm. Means that it will turn an input into an output, and the output is called the message digest. That's the technical word for it. So it takes an input message, it will hash it, whatever the mathematical operation that's being used to turn it into a different hash value. This example here, giving you a plain text, is turned into a hash value here. There are various hashing algorithms. And in order for a function or an algorithm to be considered a cryptographic hash function, it has to comply with, I think, 5 criterions. One of them is that it has to be a one-way function. It means that you will turn an input into a hash digest. However, you can't reverse it. You can't do take a hash value and turn it into the original message, right? So it's just a one-way function. The other criterion, I think, it has to be easy to compute. Easy to compute means it has to be a fast process, because here we're adding an extra cryptographic process to our communication. So that means we're increasing the overhead on our network. So it must be fast, right? So if it's not fast, then this defeats the purpose and it's making our communication slower and so on. What's another criterion is that it has to be weak collision resistant and strong collision resistance. So weak collision resistance is that you cannot have, let's say, an input X and an input Y that will hash to the same value, right? So it does not matter what the message is, right, that you are hashing. Let's say like message A or message B. Let's say hello and hola. Those two messages are different. So they must have different hash digests, right? So if they hash to the same value, then they're not weak collision resistance. And strong collision resistant means that we're not talking about just 2 input messages. We're saying that any 2 messages will hash to the same value, right? So it does not matter how many messages you're going to try. There should not have 2 messages with the same hash digest. And the 5th criterion is that a hash function must have a fixed size output, right? So it does not matter the size of the input that you're hashing, whether it's like, I don't know, 1,000 bits or 2,000 bits, whatever the size is, it's always going to hash to the same size, fixed size the message digest. So these hash functions, by the way, these examples, they have a preset fixed size output, and we're going to talk about some of those examples. However, one more thing that what is it? Yeah, one more thing is that if you hash, let's say, the message and you get a certain message digest, if you hash it again, you should get the same message digest. It doesn't mean that you hashed it now and you get this, let's say, current digest, and you hash it, let's say, after 1 hour, you should always get the same message digest for the same input, right? So the same input should always hash to the same value. Let me just actually look up, I think SHA-1, which is Secure Hash Algorithm 1. I think it has a fixed size message digest of 160 bits, I think. I need to look that up in a second. Okay, let's see. So what is it? SHA-1, right? So SHA-1 digest size. Yeah, there it is. So SHA-1 is 160-bit size digest. So no matter what the input size is always going to be hashed into 160 bits. Let's see MD5. So MD5 is just another hashing function. It does generate 128-bit fixed size. And it makes sense because you're trying to compress your input, because hash functions are sometimes, or one of the main purposes of them is to generate signatures, digital signatures. So you don't want to have a signature that is of a big size, right? So 128 bits is a acceptable size for a digital signature. Okay, so in this part, I'm going to give you two actually examples of crypto systems. Crypto system is a cryptographic algorithm. That's what it means. Crypto system is a cryptographic algorithm. So the first crypto system that we're going to take a look at is called Caesar Cipher. So Caesar Cipher, by the way, one more time. Crypto system is equal to cipher is equal to crypto algorithm, right? They just all mean the same thing, but knowing the terminology is important. So it is known. So the Caesar cipher, first of all, a little bit of history about it. So the Caesar cipher, which is said to have been used by Julius Caesar, right, to communicate with his army, right, back at the old ages in the Roman Empire. So Caesar is considered actually to be one of the first persons to have ever employed encryption for the sake of security messages. So Caesar decided that shifting each letter in the message would be his standard algorithm. Like, let's say like his message is like attack tonight, right? What he does is that he will shift each character, let's say like 3 spaces, and it will generate what we call a ciphertext. And you will send that with, let's say, one of his, I don't know, generals. And once it reaches the destination, they will be able to decode it back because they're the only people that know that we're using this mechanism, right? Which is of the shifting mechanism of 3 letters. Now, the thing is that the value for the shift is called the key. That's the key parameter. And the crypto system that we're using is called the Caesar cipher. So without knowing the crypto system and the key, you're never going to be able to decrypt this, right? Unless you're just guessing and guessing, and maybe you end up with a correct guess and maybe not. So one thing you should remember about the Caesar cipher is that it is considered to be called a substitution cipher. What that means is that units of plain text in the original message will be transformed or replaced. So substitution, it will be substituted, replaced with new units of text. So let's take a look at an example here. For that, let me actually exit the, okay. So let's take a look at an example. Suppose that we're using the Caesar cipher to encrypt this plain text, right? So let's say Dr. Callahan wants us to conduct an attack tonight, right, at dawn, right? So he says, I'm going to send this message to Professor Arfawi, and I'm going to encrypt it so no one knows about our attack. So in this case, Dr. Callahan is Julius Caesar, is the emperor. So attack at dawn with a key 3. I've chosen 3, but you can choose any value from, let's say, any integer value. Does not matter what that integer value is. By the way, we're not limited to just 26 because we have 26 characters. There could be a way of, let's say, if it spills over 26, we're just going to do mod 26, and that's going to take us back to the beginning of the alphabet. Don't confuse yourself with that. But for now, pick an integer value, and that's going to be your shift value, right? So that's going to be the key. And the plain text is here, attack at dawn, right? So the first thing that we're going to do in this algorithm is that we're going to put down our alphabet, A through Z, in this grid. And the next thing is to use the key value 3 to shift or create what we call a cipher alphabet. And that means we're going to shift 3 characters, say 3 characters here. We're going to shift them towards the end of my cipher alphabet. And then I'm just going to append the rest of the alphabet at the beginning here, right? So now I'm generating what I call a cipher alphabet, right? So based on this 3 value, I shifted 3 characters, okay? So this is my plain alphabet, and this is my cipher alphabet. And the process is to take each one of these characters and match it or substitute it with a cipher character, right? So A from the plain alphabet is matched with D. So now A is going to be turned into D. Then T is going to be turned into W, right? So T is going to be turned into W twice. And then we have A, which we figure that is D. And then C is going to be turned into F. So that is the next character. And then K is going to be turned into N. Okay, so that's N. You have a space, I could leave a space. And then A, which is D. And then T, which is W. We figured that from before. And then we have D. D is going to encode into G. Okay, so I put G here. And then we have A, which is D, and then W, which is Z. Now, make sure you guys don't get confused by going from plain to cipher. Don't go from cipher to plain because you are enciphering. And when you're enciphering, you're going from plain alphabet to cipher alphabet. So that gave me ZW, right? So it's not really this W will be turned into T. It's actually this W will be turned into Z. And then N, which is going to be the plain N, will be turned into Q, the cipher Q, right? So this is the ciphertext. So if let's say there's a man-in-the-middle attack, and that's eavesdropping, let's say someone, and reads this message, they're not going to be able to know what that really message means, right? So without knowing the crypto system and the key value, this is meaningless to anyone, right? So that is the encryption process with Caesar Cipher. And let's take a look at the decryption process. So I forgot, to be honest, I put this slide a long time ago, and I even forgot what this really, encrypts to, decrypts to. So let's find out. That makes it more exciting. Okay, so the decryption process is actually to go in reverse order. Means that we're going from the cipher alphabet to the plain alphabet. But before we do that, we need to generate our cipher alphabet. Same as before. Here we're using key 3 because this is a symmetric key. The sender of this message gave me this as a key. Says, hey, I used key 3 to encrypt this. Use that same symmetric key to decrypt it. Okay, so we're talking about symmetric key crypto here. Okay, so let's see. Let's generate an alphabet. So ABC, that's a shift of 3. It's not always 3, by the way. So don't think that it's always 3. Okay, so now I generated my cyber. Oh, damn it. I copied and empty. Okay, so now this is my cipher alphabet. Now we're going in this order, right? We're going in this direction. So we're going from cipher to plain. So the first character here is U, and U is right here, and it will be turned into R. Okay, and what's the next character? That is H. H will be turned into E, and W is going to be turned into T. And then X is going to be right here, turned into U. And then U is going to be turned into R. And then A is turned into X. Is it true? No, what? Wait, am I missing something here? Did I do a boo-boo somewhere? Wait, so R, so that's U, right? So yeah, so X is U, and then U is R, and then A, which is this. I think that is a mistake somewhere. Okay. And then we have W. W is going to turn into T, and R is going to be turned into O. And then U is going to be turned into R, and then R is going to be turned into O, and then P is going to be turned into, this is P right here, turned into M, and then H is E. So it's supposedly the message is return to Rome, right? That's the encrypted message that was sent. And this is the plain text. So this is the ciphertext, that's the plain text. I think what's happening here is that was just an extra character, that A there. However, someone could inject it there just to confuse, anyone else that's trying to decrypt this, make it even more sophisticated by injecting extra characters. The Enigma machine from WW2 used a substitution cipher, right? I think so. Yes, I think so. Yeah, they did. What did Dr. Callahan give us? Famous Sherlock Holmes story with substitution cipher. Yeah, I mean that sounds interesting. Okay, let's go to the next actually cipher. This is rail fence cipher. A rail fence cipher, by the way, and a little bit of history about it, is that the first uses of this cipher are traced back to the ancient Greeks. We're not talking about Romans here, we're talking about Greeks. So remember, talking about huge empires, and at that time, data security is an issue. So, inventing a way to make it more secure was a major goal. So they used a device called Escitoli, right? This is called a Escitoli, which rhymes with Italy. And to encrypt and send messages. That's what they use. So this Escitoli, it is also called a transposition machine. Okay, it is comprised of a cylinder and a parchment. So you have a cylinder here and you have a parchment, and it's similar to a ribbon. This parchment, which was wrapped around the cylinder, and the message to be, encrypted was then written on the coiled ribbon. So this is also considered actually not also, but this is considered a transposition cipher. What that means is that it does not involve substitution of characters. However, it involves the rearrangement of characters. Okay, so say Caesar cipher does substitution, and Railfence does the rearrangement. It's going to just mix and rearrange the characters based on a certain algorithm. So this is, I put down basically the steps for the encryption algorithm and the steps for decryption. Let's follow these steps in this example. So the idea for encryption, let's say we want to encrypt this message, this plain text, defend the east wall, and we chose a key 4, just to keep it simple for our example. Our goal is to create a ciphertext. We're going to follow this algorithm. So the algorithm is that you need to generate or create a grid, and the grid dimensions, let's say columns by rows, columns will be determined based on the number of characters in this message, in this plain text, the number of characters. So you can count your characters, and based on the characters, you're going to have a number of columns. And the number of rows in this grid is just based on the key value here. So this is 4, it means we have 4 rows. And the number of columns are based on the number of characters. Let me find out if we got the right dimensions here. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And this is, let's say, 5, 10, and 15, 20. Okay, so we have 20 here, 20 columns and 4 rows because we have a key 4. There is something that we should all pay attention to. You see where we have spaces? It is recommended that we substitute spaces with a special character when using rearrangement of characters, because if you use spaces, you may end up confusing yourself, and you may even forget about some of these spaces, so you get out of order arrangement. So let's put like @ symbol as in space. So basically we agreed with the receiver of this message that a space is referred to it by this @ symbol, for example. So it's a special character that is not part of our alphabet. However, it will symbolize space. So let's see what this is going to turn into. So the next step is to mark a zigzag pattern. So the zigzag pattern like this, so you're going to mark it. And later on, we're going to place our characters based on that. So you're going to mark the zigzag pattern in your grid like this. This is one more. So this is a zigzag here pattern, and we're going to place these characters following that pattern, right? So going in this pattern, we're going to place our characters. Okay, let's place the characters. So the first character is D. The next character is E. Oops. So the next character is E. The next character is F. They're automatically turned into caps, so don't worry about that. E, and then N. Make sure you guys correct me if I forget a character or something. I usually do that. And then space, and then T, and then H, and then E. And then here we have a space. Okay, so that's east wall. So that's E. Okay, east. And then we have that. And then W, A, and then L. Oops, L and L. Okay, so now that we place the characters following the zigzag pattern, the next thing to do, which is the final step of this algorithm, is to read the characters one row at a time, right? So let's find out what the characters are in the first row. This is the first row. And the characters are D, oh wait, space, D at A, L, right? And then the next row is going to give me E, D, T, E, S, A, L. And the next is going to give me F, N, H at T, W. And then the next row, the last row, gives me E, E, and then at. So you see, like, if you ignored the spaces, see that space here, you wouldn't have known that there is a space there. And you probably would have ignored it. And the person who's intended to decrypt this may end up with a wrong message. So this is how you encrypt. That is using rail fence cipher. So the process is that you follow these steps: is create the grid based on the rows and the columns that are number of characters by key value, integer value, and then mark the zigzag pattern, and then place the characters following that pattern. And then you're going to read the characters one row at a time, and that gives you the ciphertext. There's no way that you will be able to know that means this without knowing the ciphertext and a cipher and the key. So let's take a look here. Now we're going to do decryption, and we're going to decrypt this ciphertext. The decryption algorithm is a little bit similar to the encryption. However, there's one step that is different. So we were told, the receivers, we are the recipients of this message. So we were given this key value, which is 4, which means that we are creating a grid of 4 rows. Now we need to determine the number of columns. We're going to count how many characters are here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And that means we have 12 columns. Okay. Now we created our grid. The next thing is to mark the pattern, right? So I'm going to put that pattern here. This is decryption. Okay. Again, this is not encryption. Okay, and the next thing is that we are going to place the characters one row at a time. Remember, in encryption, we followed the pattern when placing the characters. When decrypting, we're actually going to place them one row at a time. So this is H goes here, and then P goes here, and then E will go in the next marked cell, which is here. So this is E, and then there's a $, and I think that is just to say that's a space character. This is E, and this is E. And then this is L, and this is O. This is O. This is L. And here we have L and P, right? And the last thing is that we're going to read the characters following this pattern now in the zigzag direction, right? So we're going to read them in this direction. Okay, so the first character is H and E, L, L, O, and then $. and then P-E-O-P-L-E. So that's basically saying hello, people, right? So that's what the plain text that was sent to us really meant. So by looking at this, it's hard to determine what that really means. So by following the algorithm of decryption, you will turn it into this. Okay, so that was just another sample or flavor of crypto systems that is real fence. Okay, just remember that key value here is 4 because we wanted a simple, example. However, that could be a bigger integer value that's going to increase the number of rows. And the characters in the ciphertext are not usually just simply as hello, people. That could be a whole paragraph. So you're going to end up with something that is totally hard to figure out without knowing these parameters. Okay, so in this part, I'm going to walk you through the process of implementing the Caesar Cipher crypto system in Java. So we're going to create a Java program that implements the Caesar Cipher. And then if we have time, I'll do it in C++ as well. It's actually quick in C++. So I'm using NetBeans for my IDE, Java development environment. You don't have to be familiar with Java really to understand this because it's really turning the algorithm into code. That's all we're doing here. Okay, so what is the process? This is a Caesar cipher. It does encryption and decryption, correct? That means we're going to need a method or a function that does the encryption and a method that does the decryption. So let's create the first method. So we're going to need a public static, let's say, public static void encoding, right? So we're going to have an encoding method. And also we're going to need a method for decoding. So public static decoding, right? So that's the second method. So we have two methods here. This has got to be a return type void. Okay. So we have two methods, one for encoding, one for decoding. Yes, for sure, Lee, just once I'm done, I'm going to have you share your code for Caesar Cipher in Python. I'm actually going to allow you to do that. Okay. Allow you to share your screen, I meant. Okay, so also we need an alphabet. So I'm going to create a global variable so that these two methods can use it. So I'm going to create a static variable that is global of type string. Okay, so static string alphabet, I'm going to call it. And I'm going to make it equal to the alphabet, right? What is it? So it's A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, and Z. The reason why I know the alphabet is because I learned it from like my child's cartoons. Something I watch it every day. I probably hear this over and over again, like 1,000 times a day. Yeah, it's actually running right now in my head. So encoding, so what are the ingredients really for the encoding algorithm? We need a key value and we need the message that we're going to encode. So the message is of type string, so that's the plain text. And we're going to need the second parameter is the key, which is an integer value. So we're going to need a key. Okay, so next thing, something that I usually do, because I can't predict what the user is going to type for me, maybe caps or lowercase, because I'm dependent here on ASCII values. I'm actually going to, actually not dependent on ASCII values, but what I'm going to do is that whatever they give me as users, I'm going to turn them into lowercase. Whether it's uppercase or lowercase, automatically they will be turned into lowercase. So the plain text that the user will give me, I'm going to make it, let's say, ptext dot 2 lower, right? So that's 2 lowercase. That's going to turn it into lowercase. By the way, C++ version of this is much easier. And then I'm going to create a variable of type string that's going to be for my ciphertext, and that's what I'm going to return, right? So I'm going to initialize it to an empty string, and that's what I'm going to, because this, actually, I'm going to make this return a string. So that's the string is going to be returning is the ciphertext. So I'm going to make it return the ctext, right? So far, we haven't generated the ctext. However, we're going to return it once it's generated. Okay. So the next thing that I want to do is to actually do the encoding process. Now that I have all my parameters, so I'm going to use a for loop to loop through the message that the user will give me. So I'm going to initialize it to, so int I starts at index 0, and I should go all the way to the plain text's length. That means it's going to get to the last index, the upper bound index of my string text that I am going to encode. Okay. And it's okay. So what does the looping process do? It's going to take, let's say, the character index. So I'm going to find the character index, the index of each one of those characters in my alphabet. So it's alphabet, spell it right? So alphabet is my variable. I'm going to get the index of, so it's the index of my plain text dot char at I. So what this does is actually going to find out the index of each one of the characters that I have in the plain text that I received from them, the user. I'm going to find their index in my alphabet. If they, let's say, like the message is hello, that means H. Let me find out the index of H in my alphabet, which is basically, what is it? 0, 1, 2, 3, 4, 5, 6, 7. So H is at index 7. So that's what this is going to capture. It's going to capture that index. And then we're going to do int, let's say, new index. So the new index is basically now the index that I want my character to be at, right? I'm going to generate a new index because I'm shifting, right? So I'm shifting my characters. So it's going to be the character index that I got from before, right? So the character index that I generated from the previous line, plus the key value, right? So if the index is 7, and I want to shift it by 3, it's going to be plus the key. So it's going to be, the new index is going to be 7. 7 plus 3, which is going to be 10. However, if let's say the users have decided to give me a key that exceeds, let's say, I don't know, the total of 26, because I want to be within that index range, 0 to 26. Therefore, let's just do mod 26. That's going to bring you back to the, if it's like 27, the result of that index, it will basically, by doing 27 mod 26, it will give you the index 1. It'll take you back to the beginning. And then we're going now to generate the character at the new indexes. So I'm going to use a char, and that's going to be ciphertext, or actually I'm going to call it cipher char. So the cipher char is now equal to the alphabet dot character at the new index, right? So char at the new index is new index. By the way, just so you know, and keep this in mind, this is just one way of doing it. There are thousands of ways of implementing the Caesar cipher algorithm. So don't think that this is the only way. Okay, now the last thing that we're going to do is that ctext is going to equal to what? It's going to equal to whatever. We're basically going to, because ctext is a string, and now we're going to assemble all the characters that we get, from this line, because we are looping. That means we're going to generate multiple numbers of characters. So let's just assemble them. And that is cipher char. Yeah, cipher char. That's what I called it. Okay. Okay, so this is my encoding method. So this is going to do the encoding for me. Okay, so now I finished my encoding. Let's do the decoding. So decoding is similar to encoding, except that we're going to reverse, instead of like, generating ciphertext or generating a plaintext. So the ingredients here will be the string ctext, the ciphertext, and also the key, because this is symmetric key crypto, so we need a key. All right, so actually it's very similar to, I may copy this and change it. Hold on. Should I do that? Maybe not. Okay, so the first thing is actually to turn everything to lowercase. So ctext is equal to ctext.lower. Okay, .toLower. Okay, that's going to do the same thing, turn it into lowercase. The next thing to do is to create our string ciphertext, right? So that is ptext. So this is going to be initialized to an empty string, and we're returning that. So we're going to return our plain text. So once we generate it, we will return it. Okay, so for this, we're going to use a for loop like before. And the for loop is similar to this. Let me just copy that. And except that this is ctext. Okay, so it's going to loop through the characters of this ctext. And what's it going to do? It's going to generate the characters like before. So I'm going to copy this. And I'm only going to change this to ctext. I'm getting the characters of my ctext. And the next thing I'm going to do is to generate the new index like this, right? So the new index, you know, in the encoding we're shifting, and in the decoding we're also shifting, but we're just shifting in the reverse order. We're shifting back. Okay, so that is okay. New index equals to char index. Okay, and the next thing is that we're going to actually have an if statement that's going to find out if the index that we found is actually less than 0, because if so, it may end up giving me a negative index, and this is a validation step here. So if new index is less than 0, what should I be doing? I should then say that the new index value is equal to my alphabet dot length, right? Plus new index, right? So that is, if it's let's say like -5, it's going to be 26 plus -5, and that means the index is going to become 21 instead. Okay. And the next thing is going to be to generate the characters for my plain text. So plain char is equal to my alphabet. Oops, spell it right, man. So my alphabet dot what is it? Dot char at, like we did earlier. Char at new index. New index that we figured out. Okay. And lastly is to just assemble these characters. Any number mod n is always positive. Is it? Yeah, it is true. However, yep, that is true. That means that step was just extra. Me thinking that I maybe get a negative number, so that's why I did that. However, you probably could just ignore that if statement part. Okay, so ptext plus plain text. That's the last thing we're going to do. Okay, and this is basically, did I plain char? Yeah, plain char. Okay, so now that I finished my encoding and decoding method, I'm just basically going to use them now. Okay, so where do I use them? I use them in the main method. Maybe the first thing that I want to do is to, because I want to prompt the users to input values, so I'm going to use a Java scanner. Equals new scanner, and it is of type system in. Okay, so I'm using a scanner so I can get user input through the console window. And so I'm going to prompt the users with a system out. Those who are, Python users, you're probably spoiled with the fact that you don't have to type all this code. You just simply type print and it will give you whatever you want. So that technically, this is a lot more work than what you would expect in Python. So let's say enter plaintext. And you're going to collect the value through the scanner. So we're going to do, so string, let's say plain is equal to through the scanner, scan dot, because this is, so it's the next line. Yeah, that's what we're going to use. And we're also going to prompt them to give us the key. So I'm going to copy this and just edit it. Copying and pasting should be a friend. So that's Palin. Okay, plain. And this will be enter key. Okay. Let's make it look better. All right, and then this is going to be an integer value. So I'm going to make it int key. And it's going to be next int, not next line. Okay, so that's prompting the users to give me the plaintext and also to give me the key. Now that they gave me the plaintext and the key, I'm going to use my functions to generate these outcomes. So I'm actually going to create a string variable here. And I'm going to call it, let's say, ciphertext. And I'm going to make it equal to the return value of the encoding method. So encoding method takes the plain that I got from the user and the key as well. And it will return for me the encoded value, and it will be stored in this variable. And therefore, I could display it now with a system out print. All right, so I'm going to print it out. So I'm going to print line instead of print. Actually, just, yeah, it doesn't matter. And maybe I put a \n here. Okay. Okay, and we're going to say that the cipher, let's say, text is. Okay, and we're going to say ciphertext, which is in the variable ciphertext. All right, so that's going to, I misspelled it, right? Okay, I'm pretty sure I did. Cipher. And then also we're going to have a message doing the displaying the decoded, just to make sure that we did the right thing. So we're going to say the plain text is, and we're going to use the decoding method here. So I'm going to say decoding, decoding, and this should take the ciphertext that we have in our variable ciphertext and the key as well, same key. All right, let's test this out. Enough with the coding. So if I run this, of course, you're going to see everything in a console window here. So here's prompting me to enter a plain text. So I'm just going to put, hello. Let's say hello, just hello people. Yeah, spell people right. Okay, and press the enter key. It says, give me a key. Let's use a shift of 5 and see here. Oh, there's something wrong in my code, I think. Because the ciphertext is this, however, my plain text is that. That means there's something wrong. Let's see. It didn't actually equal out. Oh, did anyone catch an error? Hold on, let me see the logical error. In my encoding, first of all. All right, so index, okay, that's should be fine. Actually, let me debug it this way. So A, B, C, D, and then 2. So the encoding is correct, C, D, F. However, this is wrong. So decoding is the problem. So decoding. All right, so we're going from I see text that line.
the new index, I think you want to subtract the key for the decoding instead.
Yes. Thank you, thank you, thank you so much for capturing that. And that's why I was basically, wait. Yeah, that's why I was doing this if statement, assuming that maybe the key value would be greater and then, and Callahan says that, okay, that's fine. But that was the only error there. That's not really. So if I put A, B, C, D, E, F, G, and put a key, let's say 2. So this is C, D, E, F, G, H, I. Well, that's a shift of 2 characters, right? And this is like the original message saying that this decodes to that. So that means we're good. So let me run it with something more meaningful. So I'm going to say, hello, people, because I would like to greet you. And then I'm going, yeah, I misspelled it again. I'm going to put a key 12. And notice this is what we get as the key and this. Now, one thing about the space here is that I haven't added code to handle spaces. So therefore, a space will be automatically, shifted, replaced with a character. In this case, I think it was Z. However, if we were to handle it, we have to add code that will handle space characters, because I'm only dependent on these characters in my alphabet. So when typing, let's say your plain text, let's eliminate spaces. So you could say, this is a message, right? So, and then you just use, let's say, key 9. Notice that it will not give you the wrong decrypted message. So this is the encryption, and this is the result of the decryption. So that's just that my algorithm does not handle spaces. You guys can improve on that. Okay, so this is 10:30 right now. So I'm going to just show you the C++ code. I'm not going to walk you through the process of encoding it, just because of time constraint, to allow some time for Q&A, and also to allow for one of your classmates to also share their code. Okay, so I think I have a project already. Let me see. That is C++ Cipher. Okay, so yeah. So the idea here is that also we have an encrypt method and decrypt function in C++, we call them. So it's a much simpler process, is that you're going to loop through the whole set of characters in the plaintext when encrypting. And this process is basically just going to be shifting the characters in the plaintext string, the plain string. And this does the opposite by subtracting, right? And here I'm just basically adding my output messages, and so I'm just going to run it just to show you what that would look like. So plain text, for example, secret. By the way, this C++ code handles spaces. Yeah, because it's doing it in a different way. It's not really working with it's not the same way. It's not working with an alphabet. It's actually just simply shifting the positions of these characters. So it's not really going back to the alphabet, finding out their indexes, coming back, generating new indexes like we did in Java. The algorithm that we're implementing in C++ here is simply just shifting the characters. Just go ahead and substitute character number 3 with character number 1, and so on, based on the key, of course. So secret message. And let's put like a key 8. So the encrypted message is this. I am not happy with what I got. Let's see. Yeah, well, I am happy now. So notice that this is the encryption, the encrypted version of that. And this is when we decrypt this, we get this, which is basically our original message. Same key, which is 8. All right, so that was just 2 implementations. You guys I will share the code with you if you want to, if you're interested.